Welcome. The following presentation is intended to provide a summary of the Olympus NDT PV series for wind energy weld tower inspections. The complete solution-based offering has been successful for many customers needing to inspect tower welds with added value including increased inspection speed, auditable data, probability of detection, and accurate repair and accept-reject information, all leading to better weld quality. The goal is to give a concise overview to the market, application, and the complete PV solution as it relates to these components. The PV100 is a complete product offering geared towards complete weld inspection with encoded data. The solution is made up of an acquisition unit, a scanner, all applicable probes and wedges, and other accessories, as well as setup and analysis tools. The actual components can vary by customer, applicable components, codes, and other needs. The solution is either a semi-automatic, meaning encoded but operator driven, or fully automatic solution. PV stands for pressure vessel, as it was originally derived to fill pressure vessel oriented codes like ASME code case 2235-9. PV100 is a generic term used freely to represent a scanning solution utilizing the combination of conventional pulse echo shear wave techniques along with TOFT, or time of flight diffraction. The solution provides volumetric weld inspection for in-service and newly manufactured welds. Based on code and coverage requirements, other techniques, including creeping waves, double zone TOFT, etc., can also be part of the total PV solution. There are actually several prepackaged solutions to start from when examining a customer's requirements. They are split up by the thickness of the weld to be inspected. It can be tailored to fit any number of other customer requirements as needed. As mentioned, the PV100 can vary in the exact technique employed. The main deciding factor is code requirements and part thickness. Windmill tower bases are typically tapering in nature. Each individual section is usually welded to a slightly thicker section, which is usually a millimeter or two thicker than the previous or lower section. The main techniques for most thicknesses are TOFT and shear wave pulse echo. As the thicknesses increase, we utilize other techniques like creeping waves and focus sets of TOFT to comply with the code and get sufficient coverage. Typical wall thicknesses seen for windmill tower bases is 12 to 46 millimeter, but can vary by tower design as well as manufacturer. Most windmill complete towers encompass the PV100 and possibly the PV100 101 range of solutions. The scanner can be reconfigured with the necessary transducers, or multiple scanners can be employed as needed. Typically, a scanner is placed on the welded component, and the component is turned mechanically to complete the scan, while an operator holds the scanner in place as shown. TOFD, or time of flight diffraction, utilizes diffracted energy versus the commonly utilized reflection technique of shear wave inspection. Using a send transducer to input the sound into the material on one side of the weld, and a receive transducer on the opposite side of the weld to listen for any sound diffracted off any weld anomalies. Because of its wide beam nature of TOFT, we are able to cover large areas of the weld with a single pair of TOFT transducers. The technique lends itself to be very sensitive to all weld anomalies, regardless of orientation, unlike pulse echo techniques. Elementary speaking, once the flaw is struck, it will vibrate and it will emit diffracted energy in all directions, allowing it to be readily detected. Height and length measurements can also be more precise than reflection techniques, since the time of flight is analyzed versus the amplitude of the reflected energy. TOFT is relatively assumed industry-wide to have two weak areas because of the wave physics. One near the surface, or the lateral wave, and one at the far surface, or back wall of the component. To overcome the weakness at the near and far surfaces, pulse echo shear wave transducers are focused at the cap and root areas. When we combine these techniques, we arrive at the PV100 solution, full volumetric weld inspection. The PV100 solution follows this technique, allowing for simultaneous cap, root, and volume inspection, giving full coverage with a single data set. All probe positions and angles are input, linking the individual channels into a single acquisition file in one scan or circumferential passer on the weld. When either acquired or post-analyzed in TomoView software, all channels are visible at one time. Side views are typically utilized for both the TOFT and shear wave channels. Both defects and other indications, including the back wall, loss of coupling, interruption by a long seam, etc., are easily recognized and identifiable. Here, a lack of sidewall fusion is shown in the TOFT channel from an actual scan from a wind tower section at a customer demo. Also seen in the image is the disruption caused by passing over a large long seam weld, which caused a jarring of the system as it passed. Here, the lack of fusion would be measured with cursors for its length and through wall height, with acceptance rejection criteria applied. When employing the PV100 system, all setups can be saved into the OmniScan for recall when applicable. For probe positioning, companies usually produce a setup chart to facilitate changing from one weld configuration to another. Because of the wide beam nature of TOFT, a single set of probes and wedges can cover a large range of thicknesses without the need for changing out equipment. Here we can see the sections from 25 mm to 50 mm all being covered with the same TOFT and shear wave probes and wedges at different index positions. Procedure development programs like ES Beam Tool facilitate proper probe and wedge selection and placement. TOFT is most often used as the main detection tool, as it is aimed at the volume of the weld, where most manufacturing defects occur. By varying the PCS, or the probe center separation, we can cover large amounts of the weld volume as seen. We see here that TOFT offers a minimal footprint with a large coverage of the weld. In addition to TOFT, shear wave probes at designated angles are aimed at the root and cap respectively, as shown here. The addition of the shear wave probes allows for full volumetric coverage of the weld. Each of the shear wave probes has its own detection channel centered around the area of interest and calibrated accordingly. Here we see the cap and root covered by respective channels from each side of the weld. As mentioned previously, as welds get thicker, we often use creeping waves to assist in code compliance and coverage. Here a scanner is shown utilizing TOFT at both the root and volume and a pair of creeping wave transducers covering the very top of the weld. The creeping wave transducers are designed and set up to cover only a few millimeters below the surface, where the first zone of TOFT will have a weakness. By refocusing the second pair of TOFT lower into the volume, we're able to get sufficient coverage and detection at the back wall area. Typically, the OmniScan platform with an 8-channel conventional ultrasonic module is used for acquisition. It can be operated directly off the mainframe or driven by a laptop with the TomoView software. The main difference between choosing to use TomoView or OmniScan only for acquisition is data display while scanning. The OmniScan will offer a single-channel view, while TomoView will allow for all acquisition channels to be viewed simultaneously while scanning. The OmniScan platform allows for further expansion into phased array ultrasonics, as well as eddy current and eddy current array technology by changing the acquisition module while keeping the same general user interface. Typically, only a semi-automatic scanner is required. The HTSM Flex offers all the necessary probe holders and other capabilities to perform the PV100 technique, including space for a preamp for the TOFT channels, water manifolds for couplant delivery, magnetic wheels, and rulers for probe positioning. It is also possible to utilize an automatic scanner like the Weld Rover to perform PV100 techniques. It is not typically required in the wind power industry, as other manufacturing steps, including automatic welding, require the component to rest on a turning system. Water is typically utilized as couplant to ensure adequate, consistent coupling during the scanning. Regulated pumps like the CFU-03 can be used, or portable manual water sprayers can also be used. Besides offering adequate coupling, because the wedges are raised slightly off the surface, we reduce wedge wear and replacement. TomoView analysis software is used to analyze all scans after acquisition. A configured industrial-style laptop can be acquired with all the necessary software to analyze and report findings. Shown above is a typical data display with TOFD data in the middle, along with shear wave channels. All channels are linked by position, so defects can be verified, analyzed, sized, and reported from multiple channels. The shear wave channels are typically set to an amplitude response palette, so defects reaching reject level can easily be discerned by color. Measurements can be acquired by cursors, gated readings, and contour boxes. The results can be reported directly out of TomoView into a Windows-friendly format for easy distribution. Depending on the customer's needs, there are a lot of smaller components that typically go into a PV100 solution as well, including cabling, probes, wedges, spare parts, etc. All necessary components can be identified based on the welds to be inspected, so a total solution package is offered. If needs change, other accessories can be added later. Umbilical or divisible cable style wiring is typically used to group all the necessary inputs into one strand. Typically, only the length, height, and position of an indication are needed for the TOF channels, but many readings exist. For the pulse echo amplitude information is also readily available. The standard report can be customized with a variety of views and readings, or screenshots can be taken for custom reports and other software programs as needed. Typically, a PV100 customer will require some additional items besides the PV100 system. These often include a code-compatible procedure, training, calibration and performance demonstration blocks, and some type of cart to hold and move the equipment. Olympus has several certified training members who offer training in theory and equipment operation, as well as Level 3 consultation, procedure writing, and job startup assistance. Performance and calibration blocks are used to calibrate the velocity, wedge delay, sensitivity, as well as any material attenuation correction needed. They are also used to demonstrate that the technique is valid and to test operators' ability to run the system and size defects adequately. These blocks typically cover a range of thicknesses. The number of blocks needed will depend on the welds being inspected and the procedure and code criteria. They typically use notches and side drill holes for calibration and demonstration capabilities. Typically 1 to 2 performance blocks will be required to cover a typical wind tower-based manufacturer's range of thicknesses. The location of calibration reflectors and other requirements of these blocks should be spelled out in the applicable procedure. In order to correctly assess the customer's needs, there are key parameters that should be identified, including the applicable code requirements, the weld type, thickness and diameter range, as well as personnel qualifications. These parameters can be identified by filling out a pre-quote form, as well as through conference calls with the applicable technical representative. A demonstration of this system can also be done on-site to help showcase the system capabilities and provide in-depth overview to the entire process. A typical demo consists of a system overview, a demo on a customer's weld, followed by a demonstration wrap-up including going through acquired data, looking at analysis and reporting tools, and also answering questions. There are many complementary documents supporting the PV100 technique and equipment solution. These include example procedures and technique charts, videos and PowerPoints, as well as example data and reports. Please contact your technical support manager for details. The PV100 solution is primarily geared towards two customers: customers who manufacture new welds and service companies who inspect welds that have already been put into service. The most common codes covering these type of welds in the United States are AWS, ASME, and API. Common applications include pressure vessels, as well as structure welds like the windmill tower base shown here, which is usually governed by AWS D1.1. The focus of this presentation will be on the wind power industry and newly manufactured welds. Windmill tower-based customers usually fall into one of two categories: either manufacturing or sub-manufacturing companies. These companies often are already inspecting the welds with conventional flaw detectors and/or radiography, as well as possibly magnetic particle and liquid penetrant inspection. Manual shear wave of these very large weldments can take hours, since the outside diameter of various sections typically varies from 14 to 40 feet. The typical output from a manual inspection is a signed report with no audible data. Radiography, while able to produce an audible output, has several disadvantages, including cost, safety, and lack of depth of flaw information, causing excessive time for repair and possible production disruption, either by having to move the component to a safe location for testing or to clear out personnel while performing the test. Inspection companies are also a great potential customer for the PV100 solution. Many tower manufacturers and sub-manufacturers have their NDT performed by these outside service providers. The cost of having a third party perform NDT services can be fairly significant, since the towers often require operators to be on site for very long periods of time to perform the services. There are many complementary applications in the wind power industry for ultrasonic flaw detectors and thickness gauges, as well as remote visual and eddy current equipment. The following few slides will show some examples. The wind tower blades are often inspected with low-frequency ultrasound with either conventional or phased array probes, and either manually or with encoding. Blades of 80 mm bond lines have been inspected successfully for flaws and bond integrity. There are also many miscellaneous weldments and subcomponents that go into a manufactured tower. An encoded system is not always practical or economical, and flaw detectors or manual phased array can be applied here. A phased array software with conventional probes has been successfully used in a lawnmower type approach to speed up large flat plate lamination inspections in comparison to manual testing. Remote visual inspection is often used when the towers are put into service to look into the gearbox and other mechanical areas for wear and cracking. For additional information on the PV100 solution, please visit the Olympus NDT website product page or contact a technical representative. Thank you for your time. I hope this presentation was helpful in showcasing how the PV100 solution is a unique testing solution for wind tower inspection requirements. For more information, please contact your local technical representative as applicable.